All right. We have an iClicker question on the right screen. Oh, no. Okay. So typically when we see uniform distribution, that means the lecture wasn't clear. So maybe it's a good thing to take a step back so we can review. We will start the class with reviewing Lance's law, and then hopefully that will help. Any other question other than Lance's law? I know many of you think that my lecture is clear, but is there any topic that you want me to cover? Or it's too early in the morning? So just the same announcements, no class on Monday. Review on Monday after the spring break. And it's your opportunity again to ask questions. Just one anecdotal evidence, the person who did the best in exam 1, he really grilled Ross really badly. And Ross is doing an amazing job. Ross is a smart guy, and he is also kind enough to organize a review session the night before the exam on Friday. There is he posted an announcement on Canvas last night. I guess quick question, how useful is the presentations sessions? Are they useful? Good. So what we are trying to do, like in ideal case, the lecture only covers the conceptual component of physics, like zero practice, zero iClicker, but based on your feedback, we incorporate some iClicker questions. And the labs are for demos, and presentation sessions are where you practice, like putting numbers, okay? But we are trying to mix things to keep you happy. Okay, no question? Kanto, do you have a question? You haven't asked me questions lately. No? Okay, good. How about you, Max? No question? Good, okay. All right, so Lance's law. So every time we see uniform distribution, that means my lecture wasn't clear at all. I was joking when I say many of you say my lecture is clear. Nobody's my lecture is clear, okay? Which is fine, you know, room for improvement. So basically, first we can start from the basic, which is there is induced EMF. This is basically voltage, okay? Is equal to negative. Negative is from Heinrich Lenz or Lenz's law, and then the coil number. In most cases, n is equal to 1, but we will see that in the case of inductors and solenoids, n is larger than 1. And then the change of magnetic flux. So this is the change of magnetic flux. Okay. So let's just have a look. So basically, if there is a change of magnetic flux, and I'm gonna draw that thing like this. This is a delta flux. This is a increase, let's say. Or the changes, sorry, this is not completely accurate because delta, non-zero delta means, okay, let's just, the flux increases. This is the external flux increases, okay? Based on Faraday's law, that means there is induced current. So increase, the flux increases. Now there are two options for the current to flow. One is clockwise, the other one is counterclockwise. Okay, either can go like this or like this. And one of them is correct, one of them is wrong, of course. So what does Lenz's law say? Okay, first we can guess, okay? Let's say the current, so again, the flux increases, this flux increases. So this one means change is larger than 0. That so so this is, I'm going to show you the wrong answer first. Okay, don't don't remember this as the right answer. Let's say the induced current point counterclockwise. Okay, that means using a right hand rule, the induced magnetic field also point up. That means the flux is even bigger. That means the I also gets bigger, and the flux inside the whole thing, induced flux plus external flux, is even bigger. That means it will generate more and more induced current. If you wait long enough, you will get infinite current. So this is the reason why this one is not correct. So the correct direction is the opposite. So this is the increasing flux. It will induce current that flows counterclockwise because of Lenz's law. And the effect of this clockwise circulating current is that it will generate induced magnetic fields that will oppose the external increases. Okay, is that clear? Or should I do a different example? So let's say this one is, the flux still goes up but decreases. So for completeness, you all know this. It's cleaner. Okay, so where does what is the direction of the current, induced current? Yeah, Sophia. Oh, because nature always like to minimize changes. So you want, so this is the guidelines. You want to generate fields that minimize changes. So the flux increases, so the loop will generate current to fight the increase of flux. Oh, why the field goes down? Because it follows right-hand rule. Good question. Yeah, the current goes clockwise. Okay. So here, the flux initially high and then low. That's what decrease means. That means, so based on Faraday's law and Lenz's law, the loop will generate currents that flows counterclockwise. This is because this current will produce flux that is in the same direction as the external flux, because the external flux decreases. So it minimizes the changes, minimize the decrease of flux by generating its own flux. So this is typically we talk in the context of magnetic field. This is the induced current. And then if you understand this, there are other cases, which is the flux point down, the flux increase or decrease. And if you know your Faraday's law cold, you should be able to figure it out. Good. So let's look at this problem. Or you want to redo this question? Okay, why don't you do that? You can discuss with your friends, okay? And I'll grade the last one. I'm curious to see the distribution. Oh, and then the direction where you see the loop matters, okay? If you look the loop from left and clockwise or counterclockwise, then if you look the same loop from the other side, then it will be the opposite. So in this case, the hint is that as this is done, the current induced in this loop as viewed from the north pole of the magnet will be good. Almost all of you got it right. So 10 more seconds. 5, 3, 2, 1. Okay. All right. So almost all of you got it right. So basically, the flux decreases in this example. And in order to minimize the changes, it needs to generate flux. I cannot annotate the screen. Basically, north and south, the flux decreases, so it needs to generate wait. When I did it last night, it was A. Square loop wire is pulled. So the flux decreases, so that's good. It's good that I didn't just skip this problem. You will get confused when you study for the exam. This is will be part of not induced. External decreases. So this one will generate induced, will want to generate induced magnetic fields that points to the right. Is that correct? Then if you look at the from this side, then the answer is counterclockwise, right? Huh? Okay, sorry. Yeah, right. Sorry. I know it's basically up to this point is correct, but you need to somehow orient yourself in 3D, and the answer is clockwise. Good. So 90% of you are smarter than me. Good. Any other question? Sophia. Oh, because the initially, the loop is lifted up. So initially, the area is like this, right? And then at t equal to non-zero, the loop will be here, let's say. And the area that interact with magnetic field is only that fraction. And then flux again is B times A. Yeah, Natalie. Oh, sometimes I move my, yeah, don't worry about lockdown browser. Just move your body. Sometimes that's the surest thing to get the answer correctly. I try to do it in my head and I get it the opposite. So if this is north, and then in order to generate magnetic field this direction, if this area is south, this area is north, and you want to generate field towards this direction, use your right hand. And the way you curl your right hand is basically clockwise direction. Yeah. Oh, good question. So on the exam, I try to, this exam too, I try to stick better to iClicker. But it doesn't mean that you can just memorize iClicker, because if that's the case, then I will test your memorization skill instead of your physics. So in the exam, I may say that this loop move downward. Then the answer is the opposite. Why is that? Because in this case, if the transition is from position 1 to position 2, that means the external flux increases. Then you want to generate induced magnetic field to reduce the change of the external flux. You need to know the rate of change of the flux, whether it increases or decreases. So if the flux stays the same, there is no induced current. Okay, so if this one is 0, then there is no induced EMF, right? Again, induced current is simply as EMF induced divided by the resistance of the loop. Okay. Good. I think it's good to move to, so one last question, if there is any. Okay, good. So that took longer than I thought. Next is we started with, let's just finish this induced current and induced magnetic field. The way we typically teach Faraday's law is this movable bar and in external magnetic field. Maybe it's a good idea to draw it before and after. So this bar is very long, and last time I gave a hint that there is a light bulb here. This is not an inductor, but this is my drawing of a light bulb. Something like that, okay? So before, after, the flux, the magnetic field stays the same, but the flux changes because there is this area difference, right? Okay. So I'm going to derive this equation here. E induced is equal to, in this configuration, is the external field times the length. The length is here. It's easier to label this region as length because when we do right-hand rule, we use L instead of width. So the width, I use the symbol L times how fast we move the bar. Okay. So this derivation, the one on the slide, is from Perusal. I think Minoru was confused why we use Lorentz force, but in physics, it's more satisfying if we can come up with a solution using different methods. Okay. So let's use red. So basically, E induced is equal to delta flux divided delta T. We only have one loop, so N is equal to 1. Okay. So minus delta, and then flux is equal to B times A divided by delta T. And then this one, B is constant. And then what remains from this part of the equation is delta A divided by delta T. So the change of area. So what is the change of area? The change of area is this one. So this area, this is the change of area, right? So what is the change of area? If you know V, if you know how fast you move the bar, what is this? So, okay, first, what is the area of a rectangle? Davis, sorry, Eli, Eli, okay. What? Length times width, good. So this one is L. What is this length here? Huh? Yeah, sorry. If you know V and delta T, what is this length here? This length here is V times delta T, right? Because you move at a constant speed. So that length is the width, like Holden says the width, but we call it this length. Sorry. This is the width and this is the length somehow. So this one is L times V times delta T, right? Divided by delta T. This one cancels. So we arrive at the same equation. Okay. So you can derive it multiple ways, whichever works. It's fine. Good. So do you want to do this iClicker or we can skip this iClicker? You want to do it? Okay. So this is very simple. I didn't even hide, like, I didn't even write the sentence. So basically, this is the formula. The exam will be more complex than this slide, by the way. So we have the same arrangement. If L is equal to 0.2 meter, V is equal to 2.5 meter per second, and B is equal to half Tesla, what is the induced EMF? Okay. Good. So 20 more seconds. Basically, the whole class get it right. 5 seconds. 3, 2, 1. Okay. So this is really straightforward. Basically, B or induced EMF is equal to B LV. I think B is half Tesla. Half Tesla. And okay, so I'll keep the unit then. V is 2.5 meter per second. So L first is trying to be cute here, but half meter, and V is 2.5. 2.5 is this, right? So this one cancel. So the answer is 1/4 volt. Okay, so the answer is B. Okay, good, very nice. I have this sometimes. Okay. So the answer is B. So next, let's talk about something useful. And typically, when we say something useful, it involves Tesla. So if you see my wife tonight, you can tell her that this Tesla joke doesn't involve my wife. So it's not even a joke. So basically, there are many giants in engineering. One of them is Thomas Alva Edison. The other one is Nikola Tesla. One thing that I forgot to mention to you, that in electrical engineering, there is DC, which is equal to, which is a abbreviation of direct current. This is the camp of Thomas Alva Edison. So for exam, the symbol for power source, like DC power supply or EMF, looks like this. You have seen it. But what you will learn today is AC. It's not air conditioner, but it's alternating currents. I think the one that you use is 120 volts. Is that correct? Different countries use slightly different voltage. The symbol for that looks like this. Okay. There will be a problem that requires you to know the symbol of AC and DC. So the reason why we use AC. Okay, so Edison is really powerful, was really powerful engineers and businessmen and scientists. Tesla, on the other hand, he was basically penniless throughout his life. So Tesla is a kind of person that just focus on advancing humanity, technology, science, doesn't care about patents, doesn't care about making companies, and doesn't care about publication. But you know, if you work hard, it doesn't go unnoticed, and we admire him a lot, including Mr. Elon Musk. So in the end, so this is the camp of Thomas Alva Edison, and this is the camp of Tesla. For powering this class, Tesla wins. So we use AC. But for your cell phone, we use DC and other small gadgets, like this keyboard, for example. Okay. The reason why Tesla wins is, I think, the last 3 slides of today's lecture. It's because when you transmit power from a generator to, let's say, this classroom, it's better to transfer that power or electricity at very high voltage, like 1,000,000 volts. And in order to increase voltage, the easiest way is using transformer like this one. We don't have time for this demo today, but we will do the other demo. And it's much easier to scale up or to increase the voltage using AC currents. And you cannot do that with DC. So for Thomas Alva Edison generator, because it makes DC, it's good for the whole room, perhaps the whole factory, but he cannot use DC to power the whole country. So that's why Tesla wins. And because he was penniless, you can read the story himself. Because he was penniless, he worked with a businessman, Mr. Westinghouse. All right, so that's a brief history of, because science doesn't occur in vacuum. So I try to share what I know about the history of physics or science in general. So right now, let's discuss about AC. So AC literally means alternating currents. So if x-axis is T and y-axis is voltage, then the voltage goes up and down. Direct currents, on the other hand, for example, your battery, a small battery, the voltage initially looks really flat. Of course, if you use it for a long time, it goes to 0. Okay. So we have discussed that changing fields, changing flux, such as in this example, can generate electricity. But this type of generator is not efficient because it requires somebody to move the bar for a long time. A more efficient methods to change flux is what kind of motion? Linear motion or rotary motion? Rotary motion. And in terms of like human, in terms of like business or in terms of practicality, the best way to do it is not with hiring undergrads to rotate this, but to use external energy such as wind, nuclear power, steam, or water. Okay. So this one, the external energy is this potential energy by this weight, but you can modify this motor by attaching a water wheel and put just dump water and it will rotate. Okay. So I want you to pay attention to the light bulb, and we will discuss what's inside this generator. Okay. Simple. Okay. So this weight has external has potential energy. I'm gonna do this. Okay. So when this weight go down, this pulley will translate linear motion into rotary motion, and what you see is that the light bulb goes up and down, meaning like lights up and go dimmer. This is because the currents or the voltage changes from high, low, high, zero, low, zero, high. So at this position, the light bulb is the brightest, and also at this position. So the reason why this one wins, because it's easier to build, it's easier to generate, that's one. And second, using transformer like that, we can increase the voltage to 1,000,000 volts for efficient transmission. So inside the generator is basically a loop. Let me change the camera 2, sorry. So this is a simulation. And let me refresh the page. So this is a simulation. If let me refresh the page. Area is quiet, there is no wind, so wind strength is equal to 0. Then the loop cannot move. If the area is quiet, there is no wind, so wind strength is equal to 0 north and south. Then the loop cannot move. Yeah, you can. And the loop is placed between a permanent magnet, north and south. This loop can rotate along one axis. Come here after the class. That when it rotates, it changes the flux. This loop can rotate along one axis, such that when it rotates, it changes the flux. To change the cosine phi here. Angular speed times cosine phi is equal to, what is this? Angular speed times delta t. Run, let's say, in a windy area, we can power a battery. So when you can run, let's say, in a windy area, you can see the current goes up and down. A battery, and using oscilloscope, you can see also the voltage using amp meter. You can see the current goes up and down. The faster the wind, using oscilloscope, you can see also the voltage goes up and down. Okay. And the current goes, the faster the wind, so unlike the higher the voltage that you can DC get. Motor. So basically, another thing that probably you know, and the current goes, is that, so unlike almost identical DC to motor. DC motor. So basically, another thing that probably you know, you notice is that this DC one looks, and then you rotate almost it yourself, identical to DC motor. So it turns out that if you DC motor take any DC motor and then you rotate it yourself, you can generate electricity. Then we need since to DC motor is DC commutator to generate, is powered by DC current, directional motion. then we need to add commutator to generate directional motion. Without commutator, your car will just go front, back, front, back, front, back. You don't want that. Oh, it's right there. Any question? Okay. What time is it now? Oh, it's right there. Okay. Go back to the slides. This is the QR code of DC motor. Let's see. And we have discussed the alternating current. So in terms of the section, the optional perusal reading, they are really optional. So we will skip AC current. Okay, good. You guys are ready for spring break? Me too. All right. So again, next let's talk something that is useful, which is wireless charging. So if you have, let's say, toothbrush, or you have wireless charging for your cell phone, how does it work? So that's the question. Okay. Any other example of the same phenomena? The name of the phenomena is mutual inductance. Anyone can help me with another example of mutual inductance? There is a hint in this slide. Who else? Killian. Yeah, what is another example of mutual inductance? The answer is right there. So induction stove. So, and be careful with induction stove, meaning like, be careful. So induction stove is basically stove that doesn't require heating elements. The nice thing is that you can put your hand on top of induction stove, and because your hand doesn't interact with magnetic field really well, you don't feel any heat. But if you use, let's say, a metallic pan, then the metallic pan will generate currents, induce currents, and if there is any currents and there is resistance, it will generate Joule heating. Okay? But be careful with that, because there are many fake induction stoves. My stove in my house looks like induction stove, but it's not. So if I touch it, I will burn my hands. Another example is transformers like that one, or like the ones near power generator. Okay. So this is fairly complex. I guess we can go through this. So mutual inductance is basically you can induce currents. Let me just summarize the topic, and then we can do derivation Monday after exam 2. Okay. So basically you have two loops. This could be your wireless charger, and another loops can be at the back of your cell phone. Okay. And in order to do mutual inductance, you flow a current here. Okay. And depending on the sign of the currents, it will generate magnetic field. Because the drawing of my loop is not that good. Well, it's kind of good. So let's say the field points this way. Okay. But one thing that is required by, we will have one more iClicker question after this, but you have to drive mechanical inductance by an AC current. You know why? Z. There is Z, there is Zain. Yeah, Z. Why we did AC power source? The answer is right there. Yeah, because you want to change the flux that the first loop generate in the second loop. So if you generate the flux, if you change the flux, if the loop one, I think on the notes I call this loop one and loop two, then if the flux due to loop one in loop two changes, then you can generate induced currents. That is also AC. Okay, so that's one. And then we will do the derivation the Monday after spring break. But based on what you learned, I have this iClicker question. If I can find it. This is actually iClicker from Harvard University, from Eric Mazur, which is a legend in physics education. So, what else? Oh, I just erased that information. So the power supply. So this is DC power supply or battery, and AC looks like this. So using what I draw here, I'm curious if you can answer this question. And using these two drawings, so the first drawing and the symbols of DC and AC, I have this iClicker question for you. So when the switch is closed, clicker, the potential difference across R is, okay. So, oh, I need to click this. And you can discuss it with your friend. Option A and B will be clear Monday after exam 2. But using these two figures, you should be able to answer that question. All right, 10 more seconds. Okay, maybe it's a bit too much. 5 seconds, just answer the question so you get some points. 3, 2, 1. Okay, so I have to apologize that I skipped many slides. But basically, one of the things that this question tests is in order to achieve mutual inductance, here we have one coil and another coil. We need to drive this circuit with an AC power supply. Okay. And this, in this drawing, the AC power supply is, no, the power supply is DC instead of AC. So the correct answer is D, but I'll give you, all of you, full credits. So I have a simple version of the problem. And then after that, I'll let you go for your spring break, okay? And I assume some of you will go immediately after you click the answer. If you want me to have office hours on Tuesday, you can stop by my office. I just want to let you know that if you need my help, I'll be in my office hours on Tuesday, but don't expect your TAs and your LAs will have office hours next week, okay? Because next week is spring break. They need a break also. Yeah, Eva. Yeah, I can have Zoom. I like Zoom better. I mean, I do stream from time to time. It's more fun. Yeah, I can have Zoom office hour on Tuesday. Okay. I mean, I've shown you some of my toy, right? Which doesn't work. Okay, so there is this. Anyway, we can hide it. Yeah, so I really enjoy teaching on Zoom, but I'm a good citizen. The department asked me to teach in person. So it's your bad luck, I think. So, okay, this is the last question before spring break. I clicker question before spring break. And then after that, you're done with me at least for one more week. So a transformer has 50 turns in the primary and 100 in the secondary. It doesn't mean anything to you right now, perhaps. That's okay. If you remember the information from Perusal, that's great. If the primary is connected to 220 volt DC supply, what will be the voltage across the secondary? This is a simpler version of this question, okay? So let's spend 30 seconds or a minute. So remember that for mutual inductance to occur, you need an AC power supply, not DC. Good. All of you are really fast. What is the answer? The answer is C. So for this inductance, if you see DC volts, that means there is no mutual inductance. All right. Have a great spring break. I'll see you in 10 days. How's that?
I know it's unrelated to the lecture today, but I need help understanding Kirchhoff's rules.
Yeah.
I don't know if you could do like a
How's
quick
that?
example on the board. I know it's unrelated to the lecture today, but I
Oh,
need
the
help
class. We can
understanding Kirchhoff's
sit after this.
rules.
Yeah. But
I don't know if you could do like a quick example on the board or not, or you gotta go or anything.
Oh, the class. We can sit after this.
Okay.
But I need to clean up the.
Okay, that's helpful. Do you need help with anything?